Välkomna till Kungliga Fysiografiska Sällskapets oktobermöte. And a special welcome tonight to our guest of honor, Professor John F. Hartwig, who is going to deliver a lecture in the memory of Sven Berggren. However, I will soon switch to Swedish because we have two items first. One is to welcome new members to the society, and the other one is that we will get a brief presentation of a project. So let's start with the introduction of new members. Vi gör det på svenska.
Ja, det går till på det sättet att jag ropar upp de nyinvalda ledamöterna och de kommer fram hit och ur presens hand mottaga diplom och ledamotsnål.
Har du mikrofon? Ja.
Jag tror jag klarar mig ändå faktiskt. Första är Magnus Becker.
Välkommen.
Tack så mycket.
Paul Börjesson. Så. Jag trodde jag hade så kraftigt.
Välkommen.
Tack så mycket.
David Dunér.
Välkommen. Ja.
Charlotta Fallvin.
Vi gör så här.
Tack så hjärtligt.
Välkommen.
Tack.
Christer Fureby.
Välkommen.
Tackar.
Hanna Isaksson.
Välkommen.
Anders Johansen.
Välkommen.
Johan Lindgren.
Välkommen.
Else Lytken.
Välkommen.
Pia Sundgren.
Välkommen.
Kristina Sundqvist.
Välkommen.
Tack så mycket.
Och David Toppgard.
Välkommen. Ja, där var listan slut. Och då går vi vidare till nästa punkt. Och då ska jag bara introducera Arne Strid, professor emeritus i botanik i Köpenhamn. Och han ska säga någonting kort om Gotlandsprojektet. Varsågod.
År 1957 påbörjade Lundadocenten Hans Runemark en serie undersökningar av floran, inte på Gotland utan på de Egeiska öarna i Grekland. Redan följande år fick han sällskap av Sven och Britt Snogerup. Hörs det? Och så börjar vi på det, ja. Okay. Ja, redan följande år, alltså 1958, fick han sällskap av paret Sven och Britt Snogerup. Hasse och Sven är dessvärre inte längre bland oss, men Britt är fortfarande den sista kvarvarande av den ursprungliga gruppen som startade projektet för 65 år sedan. Dessvärre kan hon inte vara här ikväll. På 60-talet och början av 70-talet så utvecklades det till en lite större forskargrupp med deltagare som Bengt Benzo, Roland von Bottmer, Lennart Engstrand, Mats Gustafsson och jag själv. De andra som är förståndigt folk, de insåg snart att det där med grundforskning i biodiversitet är en rätt så brödlös sysselsättning. Så efter disputationen övergick de till tillämpade delar av botaniken, framförallt växtförädling, där de gjorde hederliga karriärer och nu allihop är medlemmar av detta lärda sällskap. Själv blev jag en slags kvarsittare i Greklandsbotaniken. Först under många år vid Köpenhamns universitet, så i perioden 2000 till 2008 som föreståndare för Göteborgs botaniska trädgård och efter 2008 som pensionär och privatgeleator i en by på Fyn i Danmark. En koll i vår databas visar att mina fältdagar i Grekland uppgår till 1664 eller drygt 4,5 år. År 2016 resulterade detta i ett paper. Vetenskaplig produktion mäts ju som bekant i antal papers. Det här hette Atlas of the Aegean Flora, består av band 1 och band 2 med utbredningskartor och korta beskrivningar av samtliga arter av kärlväxter på de Egeiska öarna, vilket är cirka 3000 eller nästan dubbelt så många som i Sverige. Och nu, 7 år senare, så har det blivit ännu ett paper, den här gången över hela Grekland, och med titeln Atlas of the Hellenic Flora. Vi har det här i form av band 1 och band 2 och band 3. 2138 sidor, eller uttryckt på ett annat sätt 10,8 kilo. Dessvärre kan jag inte dela ut särtryck. Men om någon skulle vara intresserad så har jag några exemplar av ett lite mindre paper på cirka 20 sidor som heter The Botanical Exploration of Greece, som beskriver kortfattat utvecklingen från slutet av 1700-talet fram till vår tid. Även de lundensiska insatserna har fått en halv sida. Ta gärna ett exemplar av den här på väg ut. Hur kommer då fysiografen in i den här bilden? Jo, på ett rätt så viktigt sätt, för under de många åren så är jag kanske en av de medlemmar som flitigast har utnyttjat möjligheten att få resestipendier från den förträffliga Dunkerfonden. Både till fältarbete och till arbete vid olika utländska herbarier, och då framförallt i Berlin och Genève. Stort tack till Sällskapet för detta. Och om jag får använda ytterligare ett par minuter så ska jag visa några bilder av livet som Greklandsbotanist. Här har vi till vänster Hans Runemark, salig Hasse, i färd med att dosera navigationens ädla konst till fiskeskepparen Dimitros Skopolitis. Vi kan se att de har sjökortet framme. Vi befinner oss ombord på Skopolitis båt Panormitis som användes till många av de månadslånga turerna bland de Egeiska öarna på den tiden. Skopolitis blev en känd och respekterad man på de centralegeiska öarna genom att han i många år körde med postbåten. Alla kände Skopolitis. Många år senare så var en liten grupp av Runemarks gamla elever tillbaka på en mer turistbetonad resa till sina gamla jaktmarker. Och där kunde vi i hamnen på Naxos till vår glädje konstatera att den lilla färjan som nu trafikerar rutten mellan Naxos och Amorgos har fått namn efter den gamla skepparen. Så här är min kära hustru nere till vänster färdig att gå ombord i Express Skopolitis. Här har vi så en av de angenämare sidorna av botanistlivet i Grekland. Eh, 1973 flyttade jag över till Köpenhamn och där byggdes det upp en liknande forskargrupp där vi framförallt intresserade oss för floran på i de grekiska bergen. Land Rovern är inköpt på ett anslag från Carlsbergfonden. Den tjänade oss i mer än 20 år och har säkert varit på fler grekiska berg än något annat fordon. Lägg märke till växtpressarna på taket. Damen näst längst till vänster är Elista Matiado som var Greklands bästa växtsamlare. Och den unge mannen längst till vänster är Prof Hartwig som på den tiden var lektor i botanik i Köpenhamn och arbetade i synnerhet med floran på berg i nordvästra Grekland. Han är lyckligtvis fortfarande bland oss och still going strong. Så Per, du må lige rejse dig så vi kan hälsa på dig. Han har blivit en smula gråare i skägget på de 50 år som har gått, men är sig annars lik. Här har vi de lokaler i Grekland där Lunda och Köpenhamnsgruppen har samlat växter. Som synes så har vi kommit rätt vitt omkring. Bland de Egeiska öarna så är det väl, nu vet jag inte om jag kan peka här, men det är en som ligger här där ingen av oss har varit. Den ön heter Jura eller Jaros. Och det var så sent som under militärjuntans tid 1967-74 ett beryktat fångläger. Det var ingen som bodde här frivilligt. Numera är fängelset lyckligtvis nedlagt och en grekisk kollega har faktiskt gjort en botanisk inventering av ön som förväntat visade den sig vara ovanligt torr, tråkig och artfattig. Den andra botaniskt okända ön ligger här och heter Agios Georgios. Den är väl ett par kilometer lång, den är brant, svårtillgänglig, obebodd och grekiska flottan har använt den som skjutmål. Så den lär vara full av oexploderade granater. Det är inget trevligt ställe att botanisera. Åtskilliga för vetenskapen nya arter har upptäckts under våra forskningar i Grekland. Här har vi 2 av dem. Omphalodes runemarki är lågväxt och storblommig och har blivit en populär stenpartiväxt. Den lilla saginan den finns på några få grekiska berg på hög höjd i våtområden. Och blommorna är bara några millimeter så den lär inte bli någon succé som trädgårdsväxt. Han näst längst till höger med den lustiga hatten har här just blivit utnämnd till hedersdoktor vid Atens universitet och har därmed rätt officiellt att kalla sig akademiker, vilket ju betyder medlem av akademien. Enligt grekerna finns det bara en riktig akademi, det är den i Aten. Alla andra är kopior. Fysiografen är ju ett gammalt och fint sällskap, men vår akademi är trots allt 10 gånger äldre. Vår första preses var en rätt känd filosof, Sokrates heter han. Här har vi förflyttat oss samma år, det är 2017, till ett helt annat ställe i Grekland, en unik plats, nämligen Athos. Athoshalvön i nordöstra Grekland är cirka 40 kilometer lång och mellan 6 och 10 kilometer bred. Sedan 1000 år är den enbart bebodd av ortodoxa munkar. Inte bara kvinnor, men också husdjur av honkön är förbjudna på hela Athos. Det där med husdjuren är viktigt, för det betyder att man kan inte hålla kor och får och getter. Här har med andra ord inte varit betning på 1000 år, vilket är enastående i Medelhavsområdet. Vi befinner oss här, jag ska säga också att längst ut mot spetsen av halvön ligger ett isolerat kalkberg som är drygt 2000 meter högt och har en ganska unik flora. På bilden här befinner vi oss i en liten boplats som heter Kerasia som ligger just vid foten av berget. Där bor ett dussintal munkar under ledning av fader Theologos som vi ser här i mitten. Här har vi några botanister en tidig morgon som håller på att göra sig klara för den långa vandringen till toppen. 2000 meter är en seriös stigning så man ska vara rätt ung och stark för att göra det upp till toppen och ner igen på samma dag. Men drygt halvvägs finns det ett litet kapell där man kan övernatta under enkla förhållanden på betonggolvet. Lägg över ett märke till katten mellan mig och min grekiska kollega Stelios Charalambidis där längst till höger. Vi hoppas att fader Theologos inte fick syn på den för att en svart katt är som bekant en av djävulens många lömska förklädningar. Den ortodoxa kyrkan har ingen påve, men 7 patriarker. Bland vilka patriarken av Konstantinopel av tradition räknas som primus inter pares. Den nuvarande patriarken är nummer 270 i raden av ärkebiskopar över Konstantinopel. Så här kan vi tala om tradition. Det dröjer ett tag innan vi kommer upp i lika många ständiga sekreterare i Fysiografen, för att nu nämna ett jämförbart ämbete. Sommaren 2021 var det 30 år sedan patriark Bartolomeus blev utnämnd till sitt höga ämbete. Han är född på ön Imbros som ligger i nordöstra Ägäis, som numera är turkisk under namnet Götçeada, och den kvarvarande grekiska befolkningen är ganska liten. Patriarken har fortfarande ett hus på ön. Och som sagt, sommaren 2021 så hade de relativt få kvarvarande kristna på ön arrangerat en serie festligheter. Och i det sammanhanget hade jag fått en hedrande inbjudan att komma och hålla ett föredrag om växterna på det heliga berget, Athos. Patriarken intresserade sig för natur och miljö. Han fick en burk hjortronsylt från Lappland och var förnöjd med det. Hallon och björnbär kände han till, men hjortron hade han inte hört talas om. Följande dag kom också patriarken av Alexandria till festen. Han är den noble herren i vit långklänning. Och de övriga är från vänster den lokala biskopen, fader Kyrillos. Och så är det min vän Stelios, han som liknar Fidel Castro. Och min kära hustru som ju dessvärre inte kan komma med till Athos. Vi fick en förträfflig lunch. Det var en varm dag i augusti och man hade dykat upp utomhus under skuggiga parasoller. En rund och glad biskop från Kreta hade tagit med en hel dunk hembränt som han gick omkring och hällde upp av. Och alla, även patriarkerna, drack med god aptit. Den gode kretensiska prästmannen han berättade att en gång under ett besök hos den grekiska menigheten i staden Aachen i Tyskland så hade han lyckats smuggla in 5 liter raki genom att påstå i tullen att det var vatten från en helig källa på Kreta. Man kan se honom i prästkappa med guldkors och allvarlig min så heiliges Wasser, heiliges Wasser. Viktigt för de troende, de har inte fått det på flera år. Och till sist, om man tröttnade på allt det kyrkliga så fanns det i hotellhyssen en knapp där man kunde tillkalla konkurrenten som vi ser här uppe till höger.
Tusen tack. Så låt mig passa på då tillfället att uppmuntra fler att söka till Dunkerfonden. Och rapportera gärna i bilder efteråt. So now we will switch to the main point of this evening. And it's a pleasure for me to introduce Professor John F. Hartwig. He's a professor of chemistry at University of California in Berkeley. He got his PhD from University of California also, and then he had a postdoc at MIT. And he was also for 14 years a professor at Yale University. And during this period, he also developed what's called the Buchwald-Hartwig amination, which is used in organic chemistry, and I guess we will learn more about this during the lecture. So Professor Hartwig has received numerous awards, including the Willard Gibbs Award in 2015, the Wolf Prize in Chemistry in 2019, and the Arthur C. Cope Award in 2021. And tonight we are happy to hand over the award in memory of Sven Berggren. And we ask Professor Hartwig to step forward. Welcome and congratulations.
Thank you very much. Thank you. Thank you.
Professor Hartwig will now deliver his lecture, which is traditionally accompanying the award. So please.
Okay. Thank you very much. Thank you very much for the introduction. It's a real honor to be here. Thanks everyone for coming. You know, I understand that this is a prize that's not just for chemists or organic chemists, but for scientists in general. So it's a real honor, and it's great to be here. It's my first time in Lund. It's a beautiful city, and great to be, you know, back traveling in person, of course, and get to meet people and have dinner and so forth. So I'm going to tell you a little bit about what my group does. I know the audience is not all chemists, and many of you have taken organic chemistry decades ago, so I will give you an introduction really into the problem that we're working on, how synthetic chemistry, you know, affects people's lives, and then talk a little bit for chemists in the audience in the middle, and then return to some kind of future ways of thinking about how one could how one could make molecules using a combination of chemistry and biology and synthetic biology. And so I have a couple slides at the end on that kind of future view of how we could maybe do what I talk about in the beginning of the talk. So synthetic chemistry really affects everybody's life, and I have a few pictures of that. I will talk about the application of our research to pharmaceutical synthesis several places in this lecture. But really, if you just think about, you know, kind of the amazing thing is that you have this white tablet, you have a headache, and you take an aspirin tablet and your headache goes away. Or you have allergies and you take this tiny little pill, and for the entire day, your allergies, maybe they don't go away completely, but they are, you know, suppressed. And I think many of you are in the medical industry, and it's just phenomenal that you take this white tablet, which contains an organic molecule, right? The kinds of molecules I'll show you in this talk, and it has that effect. And in other areas, right, we make materials that are used for sutures or joint replacements. Half of the nitrogen atoms in your body ultimately come from the Haber-Bosch process, the synthesis of ammonia that becomes fertilizer, goes out in the plants, the animals eat the plants, you eat the animals, or you eat the plants. And the nitrogen atoms in your body that are, of course, in the proteins and the amino acids of your proteins really originated from this enormous chemical synthesis, the Haber-Bosch process. Now, we also make materials that make us safe. I went cycling today and wore a helmet to keep my head safe, or maybe put on a shirt that makes you think you can run faster or walk farther. But we also lightweight vehicles so that they get better gas mileage or they have better range for the electrical vehicles that are out there now. And if it's an electric car, you need to get power for that, and maybe you can get that power from solar energy, and it's not an organic molecule so much, but it's still chemical synthesis to make these, you know, high efficiency solar panels. And the displays, we heard about a Nobel Prize today, and nano structures that are part of displays. And so chemical synthesis, Buendi was developed a way to make those quantum dots. And so chemical synthesis is a part of those. And even things that are natural, like maybe the arms or the tables here on the, or chairs like this, are often coated with something that makes them last longer, and some of the best coatings are made through chemical synthesis. So all of your aspects of your life, things that you touch and feel, are really a part of result from chemical synthesis. I'm going to talk about organic molecules, so let me give you one slide to teach you organic chemistry, or refresh your organic chemistry, right? An atom has electrons around a nucleus. So here's our cartoon of electrons around a nucleus. And chemical bonds are formed by sharing them. And so methane, sort of becoming more famous molecule because of its greenhouse gas properties, right, has a bond between carbon and hydrogen. And that line here denotes the sharing of electrons that makes a bond there. And so we call that a carbon-hydrogen bond. And, you know, this is a kind of a representation, a space-filling model, as we call it, of methane, where the black is the carbon in the middle, the hydrogen's around the outside. And so this gives you kind of a more three-dimensional view of what this line drawing depicts. Now, most molecules, organic molecules, have more than one carbon in them, and so we draw those with this kind of chain, and so these are the carbon-carbon bonds, these lines in between. And we don't draw all the carbons and all the hydrogens and molecules because there's too many of them and it would make the picture too cluttered. So every time you see something like this, that means that denotes the carbon-carbon bonds in these molecules. Here would be octane, that would be a gasoline a component for your car. Now, some molecules most molecules don't just have carbon and hydrogen in them. For example, ethanol, which would be in the wine in dinner tonight, has oxygen in it. And so if we think about this, the properties of this molecule, it dissolves in water because it's an alcohol and has this hydroxyl group, this oxygen and a hydrogen, that makes it so ethanol dissolves in water, but of course octane does not. The salad oil, salad dressing would have oil and vinegar that are not mixed together. But this part of the molecule that gives it its water solubility and also its reactivity is called a functional group. Functional groups are an atom or a collection of atoms within a molecule that has similar properties in every molecule in which they exist. So whether it's ethanol with 2 carbons, or we could put a hydroxyl group at the end here and make it octanol, but the alcohol unit in those is going to react similarly in all of those molecules. Now, the other part of the molecule over here that has just these carbons and hydrogens is usually the part of the molecule that doesn't react. And is typically unreactive, and we often just abbreviate that with an R for radical, is what that word R comes from. And so because that part is sort of irrelevant to the reactions of the molecules, we just abbreviate that part. But what I'll show you in the middle of today is that part of what we've done is to figure out how to do reactions at these parts of the molecule instead of the typically reactive part that you would learn about in Introductory Organic Chemistry. Now, if this is going to react, what will ethanol do? Well, in the presence of oxygen, it can become acetic acid, which is vinegar, right? But it's not a reaction that occurs very fast. So to make that reaction occur faster, we add a catalyst, and the catalyst in this case is often an enzyme to convert ethanol to acetic acid, but it is something that makes the reaction faster, right? What we do is to develop catalysts. Hopefully for things more complex than ethanol to acetic acid, but if we take a few minutes to talk about what a catalyst is and what it does, so Berzelius in 1835 described catalysts in this way, so the nomenclature comes from that, and it's a reaction component that increases the rate, but is the same at the beginning and the end. And so what I'm showing down here is an energy diagram. So energy is in this direction, and the progress of the reaction is in this direction. So here are the reactants or starting materials. Here are the products. The products are more stable than the reactants, lower energy, which is why the reaction occurs at all. But the reaction doesn't occur immediately because there's an energetic barrier to this reaction. So in a sort of classical picture, if there's any physical chemists in the audience, don't harass me for what I'm about to say, because it has to do with quantum mechanics and stuff. But right, this is a little bit like the elevation map for, say, a bike ride. And this is the one that we did when we were in Berkeley. You were in Berkeley, where you'd start off at low energy, and you'd have to go over this barrier up a couple, 1,000 feet to get to the top of this. And so it requires energy to get up there, just like the reaction requires energy to get over this barrier from reactants to products. But maybe there's a better way to get from here to here, right, or to get back to there that wouldn't require such a high barrier. And that's where a catalyst comes in, because it creates a new pathway, right, that makes impossible or very slow reactions occur faster. And it usually has many more steps. So there would be all these intermediates from reactants to products, but each of the barriers for these reactions is lower than the barrier for the initial reaction without the catalyst, right? And so that's what catalysts do. And what we do is try to dream up what this pathway would be that would get from reactants to products at a faster rate with a lower energy barrier. And then if the reaction already exists, try to figure out what these intermediates are, what the transition states are between them, make it occur with a lower energy, or to have the catalyst last longer. All right, so let's go back to vinegar, right? So if we think of acetic acid, where does that come from? I told you it can come from ethanol, but if you go to the store and you buy a bottle of vinegar, probably it came from fermentation process, taking sugar and oxidizing that to acetic acid to make vinegar that you would eat. While there's a lot of salad dressing in the world, and maybe pickles, especially here, right, at breakfast, in fact, acetic acid is used for all sorts of different things. So we actually make, as a human race, we make 5 billion pounds of acetic acid per year. Just staggering numbers. And we don't want to use food to make 5 billion pounds of acetic acid. So where's it going to come from? What do we have billions and billions of pounds of? Coal. Right? So coal is what's used to make acetic acid. How do we do that? Right? We do this through a couple of steps. You take coal and you heat it at very, very high temperature in water. Coal is just carbon. Carbon plus water combines to make carbon monoxide and hydrogen. And we call this, in the chemical industry, we call it synthesis gas or syngas. And almost everything can be made this way, because we take this carbon monoxide and hydrogen, and we use a catalyst, not in our group, but in the industry. One of the largest scale chemical reactions that's done. With a catalyst, you make methanol, which is wood alcohol, don't drink methanol. And from the methanol, using its second catalyst, we make acetic acid. And this catalyst is soluble and called a homogeneous catalyst. And this is insoluble, called a heterogeneous catalyst, because it's in a different phase. And so in the chemical industry, this is how you make acetic acid. And British Petroleum is one of the companies that does this in England and plants around the world. All right, so acetic acid is a very small molecule. It's an important molecule because we make all sorts of chemicals from that. And from methanol, you can make ethylene. And from ethylene, you can make polyethylene, which is plastic. And right, that's where all this stuff is coming from. So as I just noted, there are several types of catalysts. There are there are enzymes that would be in bacteria that would do this. There's a heterogeneous catalyst used for this, and a homogeneous catalyst used for this. This being something from biology, this being a solid, and this being something that dissolves in the solution. All right, so as I said, acetic acid is a really simple molecule, but there's lots of molecules that are very important molecules that are really complicated, right? All of these lines are carbon-carbon bonds in here. Very, very complicated structure of a molecule named vancomycin. Does anybody have heard of vancomycin? So vancomycin is discovered from the dirt in the jungles of Borneo. It's made by bacteria. It was synthesized by some of the greats of synthetic organic chemistry. And it's an antibacterial, right? It's an antibiotic, and it's an antibiotic that is one might take if some of the initial antibiotics are not effective. It's like the antibiotic of last resort. So it's an extremely important molecule and used somewhat commonly. Another synthetic target for chemists like the Evans and the Nicolaus and Danishevskys and Wenders of the world is this one called Taxol. Taxol is another extremely famous molecule, a little bit more in Europe because it's synthesized by the Pacific yew tree in the western part of the United States, but it's actually made by semi-synthesis, starting with the molecule from the European yew tree discovered in Gif, south, I think it's south, right, of Paris. And so this part here, pretty complicated, amazingly is made by this tree, and then chemists put this part on the side. All right, well, fortunately, Taxol is an anti-cancer compound. Fortunately, I'm not a patient that ever took Taxol, but I did take vancomycin, right? And so I had a pneumonia case that didn't respond to the first level of antibiotics. And I'm here today because the second round worked with vancomycin, right? And if you look at here, I got 3 IVs of this, of 1.25 grams, and this synthesis by Nicolau and Evans made milligram quantities. So one might argue that this activity was of no use, right? You can't make enough vancomycin by chemical synthesis to treat anybody, let alone even one dose for a person. But we learn an enormous amount by making these types of molecules. And one thing I need to point out before we go on is that these molecules have these rings in them with 6 carbons, called benzene rings for those who've had organic chemistry a long time ago, or phenyl rings, or they're aromatic rings, often abbreviated, you'll see in my talk, as AR. And these rings are everywhere in medicinally active compounds. They're in the middle of vancomycin, they're on the outside of Taxol, and they're in probably 90% of drugs that you would take. So by learning about how to make these complex molecules, that enables chemists to make what nature doesn't. And I like to use the statins as an example, right? I have high cholesterol. Many of you might have high cholesterol and be people who take statins. Statins were discovered, again, as natural products by Endo and by Roy Vagelos, who was at Merck. And they were prescribed, and you can get a prescription for one of these statins. But the largest selling drug of all time is Lipitor. It was a Pfizer compound. And if you open up this ring, it becomes this group. And if you kind of squint, there's some 6-membered ring here that start to look like these here. And so medicinal chemists took this as a lead and developed this compound that is the #1 selling drug in history. And it has all of these 6-membered rings, and this is similar 5-membered ring in the middle. And I'm a patient of this too. I have high cholesterol. I ate egg whites for 2 years. Doesn't matter. Your body makes a certain amount of cholesterol. You take one of these tablets, boom, my cholesterol goes from like 200 to 120, right? So, this is, say, my father had several heart attacks, so I'm very happy to be able to lower my cholesterol, so I'm not going to suffer, hopefully, from heart attacks. All right, so that's the kind of thing that we can do as synthetic chemists. We can, make molecules nature won't make and have these amazing medicinal functions. All right, so I did point out that molecules like vancomycin, Taxol, they are made in organisms that have enzymes that do the catalysis. So in your body, it does make things with enzymes, right? But most, as I said, things like acetic acid are made with these enormous chemical plants with distillation towers and billions of pounds per year. Is there some middle ground, right? So could we, make the Pfizer compound that I just mentioned, using this kind of chemistry, but not on this scale and in more complex structures. And so here's an example of a molecule that became very important in the late 80s, early 90s, called indinavir, Crixivan. And so it has a structure that is more complex, right, than the statins, but not nearly as complex as vancomycin. And it has, carbons where there's a left-hand and a right-hand version of them. And it's a very difficult compound to make. But it was very important because it was the first compound that was active against HIV virus and AIDS. And so in the late 80s, early 90s, I was a student around that time in San Francisco, and it was a pretty frightening time, right? And we sort of went through another one of those times. And this was the first compound that gave some hope that there could be a medicine that would actually act against that virus, because not all viruses respond, right, to small molecules. So I just want to point out here, since it's Nobel Prize week, that carbon stereochemistry, the left versus right hand, can be set by reactions that were developed by Knowles and Noyori, who won the Nobel Prize for asymmetric catalysis. And this portion of the molecule is made by a kinetic resolution by an enzyme, and Francis Arnold a few years ago won that for the directed evolution of enzymes to be able to do reactions that would make molecules, portions of molecules like that, right? So without those developments, we wouldn't have this compound, we wouldn't have molecules that are active against AIDS. We have much better compounds now, fortunately, and I'll show you one later. But we can think about the value of the synthesis in two ways. You can have a molecule, and then you can have advances in synthesis that make it easier to make that molecule. But we as chemists, medicinal chemists, have to make a choice about what molecule to make. And what dictates that choice? So I would argue that that's dictated by the reactions that we have. If we don't have a chemical reaction to make a certain type of structure, we don't make that structure, because it's going to be very hard to do. And so I like to take the example of these sartan family of drugs that are against high blood pressure. My mother has high blood pressure and takes these drugs. Okay, so why do I say that? Well, if you're a chemist and all you have as a starting material is this central set of two rings with these two phenyl groups attached to each other, and you were given the assignment of putting something off the top and something off the side, you couldn't do it, right? You'd have to make a mess of, combination of things and have to separate them all. You could never manufacture kilograms or tons of this molecule to have these drugs, and there's a whole family of them that are what you take for high blood pressure. So why is it that we have all these drugs? Well, that's because we can make that carbon-carbon bond. We can take the top half and the bottom half and put it together by a reaction called cross-coupling. And so the way this compound would be made would be to take this compound with zinc attached to it, and this one with a bromine attached to it. This is what we call the nucleophile and the electrophile, and with this catalyst, nickel or palladium, we put that carbon-carbon bond together. And now if you gave someone who's taking a course in Introductory Organic Chemistry the problem of going from here to here, most students could do that just fine by knowing you can take this carbon and this nitrogen and put some stuff on here, and then do a radical reaction on the top and a substitution and make that, right? So that's fairly straightforward organic chemistry from there. But if you didn't have the ability to make that carbon-carbon bond, nobody would make these sartan family of drugs, and we wouldn't have this whole multi-billion-dollar sets of compounds for this. And so that's why these people won the Nobel Prize in 2010 for the development of cross-coupling, is because it can make these sorts of carbon-carbon bonds that are so common in medicinally active compounds. All right. So let's get back to the research problem that we work on, and that is to develop these kinds of catalytic pathways to address these kinds of problems that are and needs that are in synthetic chemistry. As I said, for us, it's largely in medicinal chemistry. It turns out that the reaction I'll talk about first is also used to make components of organic light-emitting diodes, right? So that's the the displays on the new iPhones here. I forgot to set my timer. So, but I can, at least there's a clock here. But the OLEDs, as they're called, the organic light emitting diodes, have amines that I'll talk about. All right, so anyway, what are the goals? Number one is to change the strategies and targets for chemical synthesis by discovering new catalysts. So if we have a new catalyst, a new reaction, we can make a new set of molecules that would have properties that are valuable. But I'm an academic, right? So I like the application, but I also really are trying to gain information that will convert this process of catalyst discovery from one that's kind of empirical to one that's more of a design process. All right, so what do our catalysts look like? I showed you the space-filling bottle of methane, carbon with 3 hydrogens. The catalysts that we make are much, much more complicated. So they have all these carbons and hydrogens that are black and white around the outside, but in the middle, this sort of orange ball would be palladium in this case. It's a metal. It's in the middle of the periodic table. And this is a phenyl group, one of those 6-membered rings that we're going to try to put into molecules. And then this would be bromine in this particular case that is going to be, was on the reagents for the cross-coupling reaction I showed you earlier. And so this just supposed to give you a picture of how the reaction's going to occur here at the palladium, but all the stuff around the outside influences the reaction rate and the lifetime of the catalyst. All right, so it was mentioned in the introduction that there's an amination reaction. An amination reaction makes a carbon-nitrogen bond in an amine. Amines have nitrogen in the middle. So the origin of one of the projects at the beginning of my career was this publication 10 years earlier by Kosugi and Megita in Japan. And this was a reaction that nobody really used, but I was interested in how palladium, that's the PD here, could form a carbon-nitrogen bond rather than a carbon-carbon bond, because there was very little chemistry of transition metals that made carbon-nitrogen or carbon-oxygen bonds. And this catalyst here with the palladium was attached to the phosphorus in this phosphine that's very large, right? So these CH3 groups point toward the metal, and there are this big grease around the catalyst, a little like I showed you in this previous slide down here. Okay. And they showed that this would work. But nobody used the reaction because it uses tin. Tin is, all these reagents are toxic. They're unstable. They can't be purified. And the scope was really narrow, and there was a lot of expensive palladium catalyst that was used. So basically, nobody used this reaction. But I found it an interesting reaction, so we started to study it. Now, from the perspective of synthesis, why would anybody care about that reaction that made that carbon-nitrogen bond? Probably what people in the room are wondering, like, who cares about making that CN bond? I'll try to convince you it's important. All right? Again, remember your organic chemistry. Right? You could take a nucleophile and an electrophile. The amine will react with a carbon that's sp3 hybridized, so it's of an alkyl iodide, and it makes ammonium salts. And those are like, you could put them to get rid of bacteria on surface, these kinds of that we all used in COVID to try to, wash our groceries that came, right? Maybe you didn't in Sweden. You guys took a different tack than we did. We washed all our groceries in the United States, right? With these antibiotics that were based on ammonium salts like this. So that's how they made them. All right. But if you have one of these 6-membered rings, right, then the substitution for the iodide doesn't work. This reaction doesn't occur. It would be downhill, right, to do that. The product's more stable than the reactant, but the barrier's really high. So you need a catalyst to make that reaction work. Okay, but prior to our work, the catalyst didn't exist. People still wanted to make these compounds. So what would you do? You would do many different reactions. You do this reaction with nitric acid that's hazardous, sometimes explodes, and then you'd go to here and many steps to get to that point. And so, people made them, but it was a long process to make those compounds. So if you had a catalyst, you could make this a bit more efficient. So you could take one of those 6-membered rings, put on a chlorine atom, or bromine or iodine, and then maybe you have a catalyst to do this. So you could take this long process and make it only 2 steps. But something I didn't appreciate but learned later is that the real importance is that nobody does that first step. Like a company does that first step. But as a synthetic chemist, you don't do that because there's 13.5 million aryl chlorides that you can buy right? Staggering kind of, right? You'll go online and you can look up that structure and find that there's millions and millions of these. So no, you don't make that. You just buy that and you buy the amine and then you would do the single step reaction to make this product that originally was many steps. And for that reason, people started making more and more of these aromatic amines, as we call them, with the carbon-nitrogen bond to an aryl ring. All right, so that is a little bit about why that isn't a reaction that one would want to catalyze, the problems about the tin reagents, but the potential in pharmaceuticals, because almost every pharmaceutical, over half of them have an aromatic carbon-nitrogen bond in them. But also something we were interested in, I'd only learned on a recent trip actually, that is really being practiced, is to use this reaction to make the whole transport layer, the positive charges going through organic light emitting diodes. And if you look up patents from Samsung and LG and maybe Apple, they all have patents that use this reaction to make those materials. And you can also make other catalysts. All right, so why are the nitrogen atoms important? I showed you, other reactions that make carbon-carbon bonds in the core of a molecule. So why are the nitrogen atoms important? Like the nitrogen atom is like 1/2 of the Velcro, right? It's the fuzzy part, and the protein would be the sticky part that would put the molecule, that would make the molecule bind to the protein. So let's take morphine as an example. So when morphine binds, and I just pulled this drawing out of here, why does it bind? It doesn't bind because it has carbons and hydrogens in it. It binds because it has oxygens and nitrogen gets protonated, so it's got a positive charge. So it goes in your brain, and it binds to the receptor, morphine receptor, and these hydrogen bond from the alcohols, but the ammonium is important because that's got a positive charge, and asp down here is aspartic acid. That's an amino acid that has a negative charge. And so the positive and negative charges makes for a salt interaction that's very strong to make morphine bind. Okay? And so that's why people so often put nitrogen atoms and oxygen atoms into molecule. It's the functional group, it's the sticky part of the molecule that makes it bind to the proteins and have their function to get rid of pain in the case of morphine. All right, so that's why we want to make carbon-nitrogen bonds. And my group and Steve Buchwald's group at MIT at the same time published that you could use a palladium catalyst, not with tin, but just an amine and a base. So this is a slightly acidic base here, strong base, to make that reaction occur with a catalyst. It was a pretty lousy reaction when we first published it, but we've worked on this reaction for decades to the point that in a way I'll show you. All right, so I won't talk about all of Steve's catalysts. Steve has done absolutely amazing work in developing palladium, the ligands that you attach to palladium to make the reaction work really well. But we've also made contributions that I'll talk about here. And the first one was, instead of having those 6-membered aromatic rings on the phosphorus in the Kosugi and Migita work, we put alkyl groups on here, very, very large ones. And that made the reactions now occur just at room temperature over a few minutes. Extremely fast reactions. The problem, though, so this was very good, but there was a problem. So I put 2 R groups here on the nitrogen. So they got 2 organic kind of groups sticking off the nitrogen. But many times you would want to have only one. And although the reaction was very fast with secondary amines, as we call them, they didn't work with primary amines that had only 1 R group. So like half of all of the amines or more in the world would not react in this reaction. So we addressed that problem by doing fundamental studies, and I'm giving sort of a quick view into what we spend most of our time on, which is making a palladium compound that has this group on it and this aryl group and the nitrogen, and I showed you that space-filling model. That's something we actually made and isolated and did a crystal structure and solved where each of the atoms are. But what we found was that if we put this ligand here on the palladium, then with just 1 R group on the nitrogen, then the carbon-nitrogen bond would form in pretty good yield. 64% of this material goes to that product. And we learned a few other things in more detail, which I guess I won't take the time to talk about. But if we take that lead and then we arrange the atoms in a little bit different way, still keeping this iron-containing backbone, Now we could make a catalyst that worked really well, would take aryl chlorides with amines, room temperature, but most important is that we could do this with just parts per million of palladium. And if we have 50 parts per million of palladium, like a palladium, a ring, or you buy an ingot or whatever you'd buy with platinum and palladium, it's expensive, right? But with this amount of palladium, the solvent is the most important, most expensive part of the reaction, right? So at this level, everything else becomes more expensive than the palladium. And so this is now what we say 18,000 turnovers. That means that you get 18,000 moles of this product for every mole of palladium that's in there. Okay? So that makes it commercially viable. Okay, and not just due to this, but again, what Buchwald's group has done is that surveys now show that this aryl halide amination, this coupling of a aryl group with an amine to make the carbon-nitrogen bond, is the most used reaction discovered in the last 4 decades. And I have to say, I can't believe that that actually came true. I was just interested in how palladium would make carbon-nitrogen bonds when we started this project, but it's turned out to have real synthetic impact. And so here are 5 compounds that are FDA-approved drugs, where one is for depression. They make that carbon-nitrogen bond through palladium and that carbon-sulfur bond. 2 of them are for hepatitis C, right? This one has this carbon-nitrogen bond. Again, this is the sticky part of the molecule for the proteins. And down here, this is an intermediate. That's another generation compound from AbbVie. This one is for solid tumors. So it's got a carbon-nitrogen bond right here, and the reason they made this compound is because you could make that bond. And then this one is most recently developed for psoriasis by Bristol Myers Squibb, and this is done with exactly the ligand I showed you on the last slide. Okay, so I want to then finish by talking about a couple topics that are sort of forward-looking. One of them has been a long-standing project in the group, and that is looking at this chemistry where we take a functional group, the aryl chloride, and replace it with an amine. So we often call this a functional group interconversion. And if you remember organic chemistry and that heavy textbook maybe some of you carried around, chapter after chapter of that book is on functional groups, alcohols, alkenes, carboxylic acids, amines, enolates, right? These are all functional group interconversions. That's sort of what an introductory course in organic chemistry is about, taking one functional group and making another, because that's where the reactions occur. So we wondered, is it possible to create a new type of organic synthesis where you put the functional group directly in at the position of the molecule that's not reactive, right? I said, like in ethanol, 1 part's reactive, 1 part's not. So that's what we tried to do recently, is take a complex structure, just denoted by having functional group, functional group, functional groups around that, and not reacting at the functional groups, but reacting at a carbon-hydrogen bond, and this one, not the ones up there, but say this one, to put in a functional group. So what are the challenges here? The challenge is getting the reaction to occur, but if it's so unreactive, maybe you need something that's extremely reactive so it just reacts everywhere in the molecule, and that's what happens with, say, chlorine or oxygen. With alkanes, you burn them in your car, right, or your furnace, and chlorination gives many products. But could we take a catalyst now and redirect this so that some reactant would react at the strongest bond and not the weaker bond where these radicals react? And if you go back to our 6-membered rings that are in so many molecules with important functions, could we change the position at which the reaction occurs, because we now catalyze it and make it go faster at a different position? All right, so I won't take too much time on this topic, and I think I have a few things in here for just chemists in the audience, if there are any, because this is some of the very latest things we've done. But we started to look at compounds with metal boron bonds, right? Borons to the left of carbon, nitrogens to the right of carbon. We were just interested in what if it's more electropositive as opposed to more electronegative. That was really what we were trying to do in the beginning. Oops. And we found that these would react with the carbon-hydrogen bond at the end of this chain I showed you in the beginning to put boron there. And I'll show you why you want to put boron there in a minute. We then made it catalytic. We have a couple percentage of rhodium in there, and we can put boron at the end of the chain at the least reactive position. But where this became practical at first was doing it again on these aromatic rings that are everywhere in medicinally active compounds. We could take one of those rings and put boron on it. And we could do that in a way that we don't have any other functional groups that are directing where the reaction occurs for the chemists in the audience. Okay, so again, we're not the only people to do that. Mitch Smith at Michigan State worked on that, but now there's hundreds of other groups that have published on this reaction. Why would you ever want to put boron in the molecule? I'll show you in a slide or two. So now we can take all of these different types of six-membered rings. Here's a functional group, here's a functional group, here's a functional group, here's a functional group, but the reaction doesn't occur there. The reaction occurs at the carbon-hydrogen bond to put a carbon-boron bond in place, right? So just taking organic chemistry and sort of turning it on its head, and instead of doing the reactions where reactions usually occur, changing the place where they occur. Doing them, and again, with tens of thousands of turnovers, and doing them on compounds that have a heteroatom, nitrogen or oxygen in the ring, and this compound, anybody recognize this core of that? That's nicotine. And you take that and put boron in it, and Pfizer did that on a 10-kilogram scale. Why did they do that? They were making a vaccine against smoking, right? So you'd grow up antibodies against that, and then you'd take this and you would no longer have a craving for nicotine. COVID took over, and Pfizer had a bigger, bigger vaccine program for COVID than for smoking. I'm not sure where this is going, but anyway, that's why they did that with that compound. So why do you want a carbon-boron bond? Well, it turns out chemists have devised all of these ways to make a carbon-boron bond into a carbon-chlorine, bromine, iodine, fluorine bond, put on carbon-carbon bonds. This is for a fluorinated alkyl group, like putting Teflon on the side, making carbon-nitrogen bonds again. So it's an extremely useful intermediate to go to all of these products, as well as Suzuki coupling that was the Nobel Prize in 2010, I guess that was, right? And so now we got this compound doravirin. It's for AIDS, right? So I showed you Crixivan before that, you know, was a pretty ineffective compound, but the first one, the latest generation from Merck is this one. And so here's this six-membered ring. How did they do that? At least for phase 2 clinical trials, they did this iridium chemistry I just showed you to put in boron, and then a reaction called oxidation to put the hydroxyl group. And so this portion here is where this portion comes from. Okay. Most recently, AstraZeneca has this compound, which is, again, for solid tumors and against solid tumors. And they use that Suzuki coupling, Nobel Prize reaction from 2010, to do this cross-coupling reactions to make the carbon-carbon bonds. But where do you get this from? You get this from this compound you just buy that. Pretty inexpensive, and you do the iridium chemistry, put in the boron, make the cross-coupling, and get this compound in a way that you would manufacture that compound. So it's come to the point where these reactions at carbon-hydrogen bonds can actually be practical. All right, so the way this occurs, and I just want to show this in brief because I gave you that energy diagram with all those steps. What are those steps? Well, this is what's in the flask. This part comes off. The carbon-hydrogen bond comes in and reacts, and the iridium inserts into that. Now you've got the aryl group from here and the boron on here, so that comes off the metal in a reductive elimination reaction to make the boron-carbon bond. And then this reacts with this compound with a boron-boron bond to make the side product and come back, right? So here's this, you know, step, 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 step. There's many steps of the reaction to put the boron in, and this is what we spent like years figuring out. This is like my passion kind of is about understanding all of the intricacies about how these reactions occur, like learning how to, you know, an engine works, and so you can tinker with it and make it work more effectively. And so that's what we've done recently. In work that was published in Science a couple of years ago, we figured out how to get a catalyst that would react at the terminal position not of a six-membered ring, but of the less reactive carbon-hydrogen bond on an end of an alkyl chain. And if you make that, you can make all of these products. All right, so how do we do that? You might imagine you can just heat something hotter if you have a high barrier, but the catalyst just decomposes. So we get almost no product here. But if we use a different, more ligand that makes the more stable complex, then we can get this in high yield. All right, but it turns out to really get this to work well, we needed to make a few changes. So we kept that core, which has all these 6-membered rings together, and we moved these methyl groups, like a portion of methane, around the side of the molecule. And what we figured out, a bit serendipitously, is if it has just one of those carbons next to the nitrogen, then it's 50 times more reactive than these others. And by learning that increased rate, that meant that we could now use the reactant, the substrate, the species that's undergoing the formation of the carbon-boron bond, not as solvent in large excess, but as one equivalent, the limiting reagent, the way that the AstraZeneca people, the Merck people are doing their reactions on arenes. So for us, this was really quite a big deal, because now you could take these molecules, again, that an alcohol, it doesn't react at the alcohol, it reacts at the carbon-hydrogen bond. You have an amine here, nitrogen with carbons on it, and that weakens the bonds here, and the catalysts usually bind to there, but this catalyst doesn't. It just goes off on the other end. So again, you have all these functional groups in these molecules. It doesn't react at the, quote, functional group, which is where we were taught reactions occur. Instead, it goes after the carbon-hydrogen bond. All right, I'll skip this next slide. So what that means is that you can now take something, okay, not as complicated as vancomycin or Taxol, but you can take a natural product made by a tree, and you can do now chemistry at positions that an enzyme would never go for. And because we made the carbon-boron bond, we can now make carbon-oxygen bonds, carbon-carbon bonds, carbon-halogen bonds, carbon-nitrogen bonds at this position of this molecule where there's no other reaction in chemistry, nothing in nature that would make the reaction occur at that position. So we call this in the community, late-stage functionalization. So at the end of a synthesis, or if you have an existing molecule that nature's making, can we change that molecule by doing reactions on it? And we can now do that even though it's got a functional group here and functional groups there. The reaction goes away from the functional group. All right, so I said I wanted to conclude by kind of a very forward-looking, well, to me it was forward-looking, view into how synthesis could be done. All right, so again, we got these complex molecules, whether it's the antibiotic vancomycin, the anti-cancer compound Taxol, or that simple molecule from a pine tree on the previous slide. Nature can make very, very complex molecules. They make it with enzymes, right? These ribbon diagrams are depictions of proteins, and there's an active site in the middle of them that often has iron, sometimes manganese, sometimes tungsten in some ones. There are enzymes that are in organisms that live in these very high pressure and high temperature regimes. We call them thermophiles or extremophiles. Right? So we're learning about all of these different organisms that make complex molecules, but they do this with limited reactions. Nature only does a few reactions, right? It makes carbon-oxygen bonds by oxidation, for example, in your liver. Could we instead put an iridium in the middle of that and make it do something different that's more like a laboratory reaction, but in the middle of an enzyme? And I'll show you that we can do it in the middle of a cell. All right, so let's, as an example of why an enzyme might be important, take this molecule over here. Okay, so there's carbons here, there's a carbon here and a carbon here. And so if this R group, as I'm saying, is just a hydrogen, then the molecule's symmetric. Okay, so I was thinking about how to explain this. Like, my two eyes, right? Just the pupils of my eyes, they're the same, right? You wouldn't be able, if you just, I'm standing here, my nose is a little crooked, but basically my eyes are the same, right? But if I had a shoe on one foot and no shoe on the other foot, then the two eyes are different because one of them is close to the shoe and this one is on the side with no shoe. But you'd never tell the difference just because, like, at the other side of my body, I might be wearing one or two shoes, right? So that's the way this molecule is. This group here, this carbon here and this carbon here, if this R group here is not a hydrogen, the back end of the molecule, or the shoes, are, has a shoe and doesn't have a shoe, but these parts are essentially the same. So how could a catalyst ever recognize this group over that group? It can't. The kinds of catalysts I just talked about, it can't. But an enzyme can do that because it has a binding site for this substrate that has a shape. So whether it binds this way or this way will depend on all of the surrounding environment. And so what we could do is evolve an enzyme so that it would selectively put this group here at that position or this group at that position. Okay, seems a little bit like only a chemist could love it kind of thing, but that's what enzymes do, and that's how they make those incredibly complex molecules, is a perfect recognition of the shapes of the molecules. And so we want to take advantage of that to say, do this carbon-carbon bond forming reaction that's nowhere in nature. It's only in the laboratory that that reaction occurs. All right, so to do that, we need, so I guess we did that here, but we did that in a flask or a test tube or a little, Eppendorf tube. Is it possible to do that in a cell? Because, for many years I've wanted to try to figure out how to get organisms to do a biosynthesis that uses laboratory chemistry. All right, so we had to create an organism. We created an E. coli that would bring, this iridium-containing unit across the cell membrane into the middle of a bacteria. That would get incorporated into a protein that by modern biochemical and molecular biology techniques is easy to overexpress, as we say, like to make large quantities of that. This goes inside that, and now that enzyme I showed you on the previous slide is now inside E. coli. And so if we add that molecule with the bromine off the side just to, having a shoe or no shoe in the back of the molecule, right, now this will react with the same selectivity in E. coli as it did in that test tube or, Eppendorf tube in the lab. So we showed that we could assemble these artificial enzymes in a cell. So then we were wondering, could we, well, if we go back a second, and this is not something that can be biosynthesized as far as I know, right? This is something we buy from a chemical supplier. But could we do this reaction on something that is biosynthesized? And so this molecule, limonene, from lemons, right, the lemon skins, has reactive portions of it that'll, again, react with that molecule I showed you on the previous slide to transfer this group to this carbon-carbon bond to make a three-membered ring. Again, biology doesn't do this. As limonene gets oxidized to carvone, and carvone's, different left-handed and right-handed carvones smell different. It's a, little problem for intro chem. But we can make this because we collaborate with Jay Kiesling, who is a synthetic biologist, and they're very good at taking the genes that would make limonene and transferring them to E. coli that I just showed you we can get the catalyst into. So we could transfer that group to make an unnatural product that would have different properties, and I don't know, someday we might make a molecule this way that's useful, but this was a proof of concept. So how do we know that it's actually made by our enzyme in that cell? Well, first, it's the only thing that will catalyze that reaction. And second, there's what we call diastereomers, left and right hands. And if we put a bunch of you together and said, two lefts and two rights and one left, right, and right, left. So those, that pattern of those diastereomers tells us it's made by our enzyme in that organism. So that was published in Nature Chemistry in 2021. And so then we wondered whether we could go a step further. Actually, I didn't think we could, but Jing Huang, who is a student postdoc working on this, knew that there are these molecules that are called diazo compounds that are from a chemical supplier, but they're actually made naturally. Pretty esoteric compounds, but azaserine looks, this part of the molecule is exactly the same as the one we were buying or making in our lab, actually making. This is made by an organism, right? It's made through a biosynthetic pathway. And so are these others. This one's actually, I think, an anti-cancer compound. So Jing's idea was that we would create this organism that would biosynthesize azaserine that looks like the ethyl diazoacetate that everybody uses in that transfer chemistry I showed you. We'd also biosynthesize the alkene that reacts with that, the styrene here, and we would, of course, make the cofactor, and we'd have iron in here, and then we would put this all together, and we'd create this organism that has this artificial biosynthetic pathway that makes an unnatural product and does so with selectivity that's controlled by this enzyme and doing this reaction that, is a laboratory reaction. It's not a reaction that usually occurs in an organism, let alone a biosynthetic pathway. So again, I don't think we're making a particularly useful molecule, but we've shown that that kind of chemistry can be done within microorganisms, and maybe we can make these more complicated and do things with this molecule afterward to make things that are actually going to have, say, medicinal value, or maybe monomers for making polymers. So this just came out in Nature and was really something that was kind of a dream of mine, to be able to take the biosynthesis and laboratory chemistry, put it together, and have organisms do that. So that's the story I wanted to tell you today about what we've done, having to do with, reversing organic chemistry to react at non-functional group portions of the molecules, and to be able to make these kinds of complex structures. So I did want to be sure to spend a few minutes to talk about, how a research group like ours works, right? I mean, I have right now about 25 to 30 students. I've had many, many people along the way who basically did all of what I talked about, and really it's their ideas that are here. So I really appreciate the recognition here, but it's really recognizing my research group over the years. And so here's a photo of the folks that are in the group now, right in front of our chemistry building. And this is a list of all the people who've worked in my lab over the years, developing the amination chemistry, the borylation chemistry, and so forth. But I also wanted to, since it's kind of an award, I wanted to acknowledge, my own mentors. I'm mentor to all of those people. But I worked for Maitland Jones at Princeton, who was an amazing teacher, and it just made me love working in the laboratory and this society and the culture and the of being in a laboratory with a group of people. And then my PhD advisors, Bob Bergman and Dick Anderson, died recently. His name ends in S-E-N, relevant, and came from North Dakota. And Steve Lippard, who was my postdoc advisor. But I also wanted to say something about my parents. This is a picture of me many years ago, graduating from college, actually. And my parents, and I mentioned my father had several heart attacks and died at a young age. So unfortunately, he hasn't sort of seen me develop in my career, but was around when I started it. But I wanted to point out here, just for fun, my mother's name is Johanna Peterson. Johanna, we go by Jo, she goes by. Peterson, S-E-N. And she was saying before I came here, my grandmother moved from Aarhus just across the water, right? And so, if you're from Aarhus and you're going to move to the United States, where do you go? So here's a map. So here's Lund, Aarhus. And so where you go is the furthest north, coldest part of the United States you can find, which is Sault Ste. Marie, Michigan, right on the Canadian border. And so my mother grew up in a town right nearby there, and we still have a cottage there. And we go there every summer with my kids. And indeed, in Escanaba, Michigan, right next to Sault Ste. Marie, there is the Swedish pantry. And I've never eaten at the Swedish pantry, but my kids went with my parents there this summer. They said it's pretty good, but we make our own Swedish pancakes. There's no lingonberry jam here, but anyway, we have I'm about, I guess, 1/8 Swedish, 1/8 Danish, quarter English, and half German, which is where my Hartwig name comes from, and my father's name, right? So I'm like Americans that have all sorts of different mixtures. So anyway, thanks so much for having me come back to Scandinavia.
Thank you so much for a fantastic lecture. I'm sure there are questions. Yes, please.
Very interesting. I wonder, these catalysts that you use, they seem very stable.
Oh, okay. Yep.
Yeah, these catalysts that you produce to accelerate your reactions, where do they go? Do they? I mean, how could I get the catalyst into myself, or is there a risk of that?
Yeah, sorry, I didn't meant to talk. So there's a couple of parts. It's different for different applications.
I understand.
For what I talked about of our own research, there's a purification step. For what in our own laboratory, we use silica, like a silicone oxygen, and we run, the compounds go through there, and the catalyst stays, and the molecules go through, and so they get purified away from the catalyst. Unfortunately, you just lose the catalyst that way, right? It doesn't get recovered. But if you are talking about the AstraZeneca or the Merck application that would be for a drug synthesis. They go through a very rigorous process to separate things. It has to be pure, right? And they crystallize, right? It's in solution, and then you recrystal. Well, actually, what you'd first do is maybe add an amino acid like cysteine, which grabs onto the palladium, or they might add something else to it that separates it out, and then you crystallize and purify. But it can be not always straightforward to get the metal out, and the Federal Food and Drug Administration and whatever the equivalent organization in Europe is has regulations about how much metal can be left in the drug, and so it gets removed in that way. Yeah. Catalyst for plastics, like for polyethylene, the catalyst is in the polyethylene actually, but it's zirconium or titanium and not so pretty innocent.
Thank you. Was there another question, Ola? Yeah. There's a microphone.
And actually for applications like the light-emitting diodes I mentioned, I assume they have to really purify that because a little bit of metal will I think, cause the quenching of the electron transport properties. And they used to use copper, and you needed so much copper to make that, it was hard to purify it. So I think that's actually been one of the reasons why it's now changed. Yeah.
Thank you very much for a very interesting talk. It seemed like or maybe I misobserved, but that the regioselectivity went down when you put your catalyst into the cell. Was that correct? And was that not surprising?
No, the regioselectivity matched, actually. I usually mention that on the previous slide. So it's 3-to-1 favoring one isomer over the other isomer.
Was it not 10-to-1 outside?
No. It was a 10-to. So yeah. So there's a 10. We stopped when there's a 10-to-1 difference. It was like 3.3 and 3.4 the other way. Multiplied them, and that was our order of magnitude difference. Right. Yeah.
Are there more
actually,
questions?
the catalyst lasts longer in the cell. Actually, higher turnover numbers in the cell. I guess it's more stable in that environment.
Okay, hi. Very nice talk. Really, really interesting to learn about catalysis. I'm wondering, when you draw your nice compounds, where everything is sitting, and you have your little connections between all of these atoms. How easy is it to get from the lab work to these very, very clean drawings? Is that how do I conceptually imagine that? When you do these experiments, how hard is it to actually figure out exactly where one thing is sitting or not sitting? Or
and I guess I should make a comment that is one thing that why I went into chemistry in the first place. Like, there's something like you just touch and feel stuff, and they're molecules. But how do we know what the structure is of the molecule, right? It's invisible to our eyes, and only now some very high-resolution techniques starting to be able to see single atoms. But for the most part, you don't see them. But so how do you figure out what any of this stuff is? It's like this mystery problem, right? So we use nuclear magnetic resonance spectroscopy. I don't know if that term means a lot to people, right? And MRI is like, what you do to look at bodies, right? But we do that to be able to figure out what atom is connected to another atom, and it can be pretty complicated for like vancomycin structure. Like they're specialists in the structure, like isolation and identification of the structures of natural products by NMR spectroscopy. Now crystallography, single crystal X-ray diffraction, is much better. Everything gets better over decades, right? And so you can get away with really, really small crystals and get a structure that shows where all the atoms are in that. And you can do it now with proteins, and you don't have to be a specialist. Actually, as a sort of anecdote, Jennifer Doudna's name, maybe from CRISPR-Cas9 work. She started her career doing crystallography on RNA, and was able to crystallize RNA in a special way and solve the first structure, I think, of tRNA was the first structure she did. But now it's become relatively routine to be able to get structures. It's not so easy to get crystals all the time. And now there's other electron diffraction ways to do that. Yeah, but it's complicated. I teach a class on how to do that.
Thank you very much. I just want to conclude by once again thanking you for a very inspiring lecture and for coming all the way here to deliver it. Thank you very much.